Howdy do. How are you folks today? All right. I'd like to introduce you to my friend Ruger. He's a good dog. At this bar, he's the most common regular at the bar. So whenever you want to eat at the bar, you have to be nice to Ruger. And he's been taught all sorts of fun tricks, like he'll stand on his hind legs and high-five you. And he's taller than you are, although you can't quite tell from this picture. But today, we're going to be talking about a watch. Have any of you been to one of these things called a scrum meeting? Right? I hear people laughing, but I don't hear anyone cheering. Do we not have a single scrum meeting fan in the audience? This is not a time for violence. That man in the corner is to be left alone. He's entitled to his opinions, however wrong. So I found myself in a situation of having a 1-hour death march of a scrum meeting first thing every morning. And during these scrum meetings, just because my time is being wasted doesn't mean that I need to be vocal about that. So I would look at my watch as the only other thing to look at than my phone. Like, you can't bring a novel to a stand-up meeting. Maybe they should change that. If there are any agile influencers in the group, I have some suggestions. So I'm looking at my watch, and then I start realizing that I could make something like this. I could make electronics that would run on a small power source, a small battery for a very long time. I could add new features to it, right? I could have a hex editor and a disassembler and a radio and all this other stuff. So when I no longer had those scrum meetings to go to each morning, I sat down and I made this. And this is the Good Watch. On the screen here, you see the hex editor. So at 8FB2, there's the value 5031. If you hold down the 4 button, it will disassemble that. That's in the flash region of memory. And you can do all sorts of cool stuff with it. There's some earlier work in this series. There's the Pluto watch. This is a reverse-engineered replacement board for the Casio F91W. This has a smaller MSP430 than I use, and it has a compass to use the extra space. So this compass allows you to tell which way is north without having to pull out your cell phone. It also has an infrared bootloader style, so you can use infrared light to replace the firmware through the front panel. In 2009, 2010, I think, this watch came out, which uses the same chip that I use, the Chipcon 430 F6147. The Chronos watch, though, is kind of big and it's kind of heavy. It's very uncomfortable to wear. And it's not really a wearable if you don't wear it. So lots of people bought this and they did cool projects with it, and then they stopped wearing it because it's horrifically uncomfortable and the plastic will dissolve in the sweat on your wrist. Another problem with this is that it's open source software, and that took off, and the community forked it and made open source software that actually built. They did a really good job with it, but the hardware design was not so open. They had a blurry JPEG image of the zoomed out schematic. So you had to sort of guess at whether what the JPEG distortion was hiding for the names of any components. And the layout was proprietary, so you couldn't manufacture a replacement board for this. You couldn't expand it into your own products. So as a hardware project, it sort of died off. It was a really cool development kit that never became something that people would wear. There's also the Faraday RF project. This uses the same chip that I use. And they also have a power amplifier. So this is intended for ham radio operations in the 900 megahertz band. They were able to get gigantic links using this, so long as they have line of sight and reasonably low interference. The firmware, the hardware, this entire design is freely available and open source. And there's another project that Mike Osmond and I played with. It's the Girltech I Am Me children's text messaging toy. And this thing was great. Do any of you have these? All right. It's a lot more popular than Scrum meetings. So this little pink text messaging toy can be reflashed, and in reflashing it, you can add a spectrum analyzer, you can open garage doors. Semi Camcar did a little thing for it called Open Sesame that just opens all the garage doors. You can use this to quickly debug different radio protocols and to sort of see whether or not you can mess with them over USB before actually committing to making custom equipment. And there's the Yardstick 1 from Great Scott Gadgets that uses a related radio core. So you can quickly prototype a radio transmitter or receiver in Python and then have it run on the air without actually using software-defined radio. And the lack of software-defined radio matters because of our power requirements. Software-defined radio is very expensive as far as your power draw goes. And we have a little coin cell that is 20 millimeters in diameter and 1.6 millimeters tall. And it needs to last for years. So let's copy a watch. When you're reverse engineering software, you generally first try to get like a code dump, and then you load it up in IDA Pro. When you're reverse engineering hardware, you begin with a pair of calipers. And you take the calipers and you measure everything about the board that you can. And you try to measure it in ways that overlap so that you'll recognize if you made a mistake by the numbers not agreeing with one another. So this is telling me that the board itself is a little bit more than 25 millimeters wide. I draw out like a mechanical diagram that shows me where things should be placed. My replacement board needs to fit in the exact same spot as the original board, and it has to connect to the same peripherals in the same locations. So it's not just enough to know where the components are. I also need accurate footprints for each of these, and I have to recreate them in my own CAD software. On the back, I have the battery connector. In each of these, I'm just sort of measuring where things go and then recreating that on the paper, so that once it's right on paper, I can then open KiCad and begin drafting it as mechanical design. At that point, I would come up with something like this. This is my initial prototype PCB. The purpose of this PCB is not to be a complete watch, although by some grace of God, it actually works as a complete watch. The purpose of this is to verify that I have the correct pinouts for the LCD screen and for the keypad. I threw a microcontroller on the watch that I chose because it would be a single package. The Chipcon 430 F6137 or 6147. There are two parts that will fit the same pad. It has 32 kilobytes of flash. That's all the code memory that I have in the world. But I can execute in place in that flash, so I don't have to copy things to RAM to run them. I also have 4 kilobytes of SRAM, which has to contain my complete state. I wrote my firmware to have no heap so that I would have perfectly deterministic memory usage, so that I won't run out of memory as the device runs, which is something that you have to do when your device is going to be running for years. Your only other option is to reboot or to garbage collect. This has a 96-segment LCD controller, which was not quite capable of lighting up everything on the LCD, but was able to get me everything that mattered. I'm missing a few elements of the day of week indicator in the upper right, and everything else is covered. It has a sub-GHz radio. The current model is tuned for 434 megahertz. Later models will do from 300 megahertz to 1 gigahertz. This allows them to receive and transmit on these bands. But this is just what the chip can support. The filter chain and the antenna also need to at least roughly match to allow the signal through. And it has a bootloader ROM, which allows me to reprogram it over a serial port. So you don't need to have an expensive JTAG debugger in order to flash this chip. You can just hook up a regular FTDI chip and some probe clips. And this was enough to bootstrap it. But I sort of skipped the part where we figured out how the LCD should be connected. An LCD is built out of common pins and segment pins. So what I did was I used sticky tape to cover them up. I took 3M sticky notes and I cut them with a razor blade. And then I covered up individual pins in order to see what would break in the final design. This board on the right is the original Casio board, in which all of the pins have been blocked that I do not have electrical support for in my own board on the left. So if I could wear a Casio watch with all of those pins covered and still use it, still have all the digits of the calculator, all the digits of the hour, all the time, if everything was still functional with those pins covered up, then everything else I can fix in software. Now, the way to figure out which is a common pin and which is a segment pin is also to cover them up. So these 4 on the far left are the common pins. If you cover up any one of these pins, roughly 1/4 of the LCD segments will refuse to light. They'll be dim and unusable. These are the segment pins. If you cover one of these up, between 1 and 4 pixels will refuse to light, but everything else is good. I need to know this electrically because these are pins that cannot be remapped on my microcontroller. But as far as like which segment or which common pin it is, all that comes from a lookup table, so that I can remap fine. So all I need to know is that these 4 are common and the rest of them are segment, and I have everything that I electrically need to wire up the entire chip. Now, if I needed to figure out which one was which, like which segments, which pixels were connected between which segment pin and which common pin, I could also go through this labor-intensive style of covering up one pin, then the next, and for each of those 4 recording which pixels disappeared. And then again for all of the segment pins, but this would take forever and a day. This is not something that would be fun to do. So a much faster solution is to make it a software problem. I connected the watch with a functional LCD wired into my early prototype board to my laptop, and then I flashed it with custom firmware, and I had the firmware light up everything. These are all the pixels that I'm able to light. Like I said, there are a few in the top right that are missing, but everything else is covered. I can show all the calculator operations, I can show all of the decimal points, I can show all of the time, all the numbers, all of that. And I go through, and by software, I then light up one common pin connected to one segment pin, and I look to see which pixel lights up. I then write C macros for this, and a lookup table, and I have a functional LCD driver without having to take photographs of the LCD under polarized light, without having to reverse engineer that physically, because I can do it by software. And the end result is a couple of C macro definitions like this that will actually write into LCD memory. The LCD memory is a peripheral, so you just write to an address in memory. You can have a pointer to it like any other pointer. And what you change there physically changes which pins of the LCD driver get lit up. And then I also have an LCD map structure, which connects each digit to the segment of its 7-segment display. And then there's an 8th for the period at the bottom. The software I rendered with the GCC toolchain, so this can compile on any vanilla Debian machine. You can build it without having to install any commercial SDKs or drivers or building your own toolchain. I also designed it so that you could flash it by a regular low-voltage serial port. So these little test clips are connecting this watch board for programming. And the regular serial port and a couple of I/O pins on the side to enter the bootloader are all that are needed to write software into this device, so that I have no strange hardware requirements or software requirements to begin developing with the project. Similarly, the number pad on the calculator watch, it has 16 buttons on the front. It can be figured out mostly by software after you figure out which pins are rows and which pins are columns. The left and the top are the I/O port numbers, so 2.2 connects to 2.3 if I press the 7 button in the top left. I then return a single byte for the scan code, where one nibble is the column and one nibble is the row. And that allows me to then tell which button is being pressed. And at the end, I have a sort of key map that then converts from the scan code in the upper half of a 16-bit word to find the lower half of the 16-bit word. The CPU is a 16-bit CPU, so whenever I say word from now on, just assume that I need 16 bits. It's the first time in my career that I've ever agreed with x86 people. Power management matters more than you would ever believe. If I were making a smartwatch or something that would be recharged every night, then I would never wear it, so my project would be a failure. So I need to know how much power each little thing in the CPU costs. And there are tricks that you can do. For example, I control all of the clocks. I can run the entire CPU off of the 32 kilohertz crystal that is intended for use as the real-time clock source. So I only get 32,000 ticks per second of the main CPU, but that's more than enough time to update the LCD every time the second counter changes. So by running the entire chip at 32 kilohertz instead of at 1 megahertz, I'm able to save power consumption. I save 155 microamps, and by dropping the usage down to only use 5 microamps. And this allows me to have a long battery life. At that point, you can begin writing simple applications. You can write a reverse Polish notation calculator. You can write a timer that just sort of sees how many seconds have elapsed since you hit the button. These are the features that you need on the watch to make it useful beyond telling time, so that I can match the features of the original Casio watch and then finally have something that's sort of worthy of wearing. There are bugs that you have to consider. And some of these are poorly documented in the radio, or in the CPU programming guide, but are documented in the errata guide. For example, the real-time clock can only be written when the program counter has certain bits set or clear. So you can't write a real-time clock driver in C, you have to write it in assembly. And you also have to know that the calling convention for the commercial compilers is backward from the GCC compiler. So you have to swap all of the registers in the code before you actually link it against your own. I added a hex editor, and this turned out to be very handy. Fuck my throat. So I'm in Budapest. I'm at the Hacktivity conference. I have no tools with me. There is a barnacle-encrusted hackerspace soldering iron, and I've managed to bum a screwdriver. And the watch on the right starts keeping very inaccurate time. It's losing minutes a day, while the watch on the left is working fine. By using the hex editor, I'm able to load up the status register of the real-time clock, and I'm able to see that they disagree by a bit. And the documentation on that laptop in the background tells me that that bit is a clock failure and that I need to handle this in software. If I'd been making this watch as like a day project that I didn't care about, that I didn't wear, that I didn't depend on the accuracy of it, it could have taken a very long time to recognize that this bug was not being properly handled. As it was, I was able to see the failure, add a safety check for it, so that the watch will recognize its own clock failures and reinitialize them, and it's no longer a problem. So you sort of have to like dog food your own code in order to recognize these reliability failures that won't hit you for weeks or months. In my case, there was a soldering mistake on the watch on the right that would cause the crystal to go out only when the air pressure changed. So every time I took a flight, the black watch would stop keeping time well. Reproducing that in a lab would not be very fun. My buddy SkyT, who financed this project, is sitting there thinking that he could reproduce this in a lab. I also added a disassembler, right? When you add things like a disassembler to code like this, there's no reason why the same code can't compile to run on your desktop. You can have unit tests or things like that that allow these projects or the libraries that they build upon to run on your regular desktop as a regular program. I can run through the entire firmware, disassemble every instruction, dump a text file, and then look to see which instructions were disassembled in order to know the accuracy of it. If the accuracy of my disassembler really mattered, this would be a really important thing to have. But for other features, like does this always compile as I'm about to merge a pull request? For that, you can have a CI server verify it in the same way that you could for a software project. There's nothing special about hardware except for the very few things that do need to run on the real machine itself, like the real-time clock bugs. I made a power-on self-test feature so that every time the watch starts up, it tries to identify any faults in itself and then list them on the screen. If it can't, for example, if the clock is wrong, the real-time clock, it'll say RTC on the screen. If the radio isn't working, that's actually an intentional backward compatibility feature. I can recognize that the radio is absent, disable the radio, and then continue as a regular radio-less watch, hiding the features that might require it. If any of you need to work in a secret volcano laboratory, you can wear the non-version radio of the watch as your local restrictions allow. Now, by this point, we have a watch that can tell time, it has a calculator, it's able to disassemble its own firmware, it's able to do all sorts of fun stuff, but there's no actual radio yet, which was sort of the point from the beginning. I want a radio tool that I can have on my wrist all the time, even in the summer, even without having to carry around something bulky. Adding a radio is covered by the datasheet for the CPU that's involved, as it's a peripheral of that CPU. You need to add a second crystal for this because it needs to be stable at much higher frequencies. And you also need a filter chain. And the filter chain is partly inside of the chip and partly outside of it. So the chip hardware can only support these frequencies. It can only do 300 to 348, then 389 to 464, then 779 to 928 megahertz. This is a lot of bandwidth. It can do a lot of different frequencies, but it can't quite do everything. So for example, it can probably recognize the frequencies of a handheld digital voice radio, but it's not able to recognize the speech that is running from my headset right now, because this is in the 500 megahertz band that is outside of the supported regions. You also need to add a filter of your own in order to prevent harmonics and to be a good citizen. Because I figured the initial audience for this project would be amateur radio operators, and forgive me, George, but they do like to complain. I wanted it to be legal within that band, so I threw in a Balin filter combined package that's very small, but restricts me to about the range 430 to 435 megahertz. I can receive outside of this range if the transmitter is very strong, like from a two-way radio, and I can transmit outside of this range if I don't mind my power being strongly reduced. In later versions, if you're a ham radio operator, if you could cover your ears, I've been considering drastically widening the filter to go from roughly 300 megahertz to 928 while also transmitting on harmonic bands. I warned you. For the antenna, there's this concept in amateur radio that there are really good antennas that are really efficient. And you'd like one of those, but you don't always have it. So sometimes you just use a random wire antenna, and then you try and fix it up on the other end. So I use the metal watch band, and that little green wire actually connects the watch band to the main PCB, so that the metal band of my watch is the antenna. This is not an efficient one, but it works in a pinch. As long as the compromises are in radio range and power, this is still a successful project. The places where I can't compromise are in the tighter requirements, like battery life or wearability. As far as the software goes, I added a graceful downgrade so that if the device powers up and finds that it has no radio, it disables all the radio features. The watch continues to function as a watch. I also added a serial port monitor so that I can use this as sort of a poor man's RF cat, so that I can prototype any radio protocol that I intend to implement on my laptop in Python, and then only later, after I have all the configuration settings correct, do I move it to running in C in a real watch. This shortens my round-trip time, because I don't need to flash the hardware or push buttons. It also allows me to script tests. So I can have my laboratory measure the output power, for example, without having to be physically present. A CI server can do it. Choosing frequencies, I have a VFO mode, so I can type in a frequency. But I also have a code plug. So I have a text file that allows me to type in useful frequencies, like the frequencies of cars in the European Union, or the frequencies of DMR radios in simplex mode. And then I have an applet on the watch that allows me to cycle between these. Radio power management matters a lot. So not only do I need to keep my CPU from using much power, but I also really need to watch the radio consumption. So at 32 kilohertz with radio off, I'm burning 5 microamps. If I jump the CPU up to 1 megahertz, I start burning a lot more than that, 160 microamps. With the radio receiving, I'm burning 15,000 microamps, 100 times as much power as just sort of sitting there. If I transmit, it's actually not much more expensive. It's only a little bit more than that. So for the radio operations, I cannot leave the radio idly receiving in the background. I will never be able to afford that without requiring the user to reflash daily. So transmitting, because it takes a shorter amount of time, can actually be cheaper than receiving. This is the amount of current consumed at any instantaneous amount of time, and doesn't consider how long the feature would need to be in the high mode. But then I have a radio. This is a photograph of an early test in a bar in West Philadelphia. We were able to transmit from the watch to the radio over Morse code, and we were able to do this from 4 city blocks away. We can also send digital beacons. So this is a 4FSK packet that is used to send the call sign of one watch to another watch. And we can interface with other hardware. So I went on Amazon and I bought all of the really cheap radio relay remote controls. You can buy these for about $15 US. For those of you coming from other continents, with electronics, that's about 45 euro, plus the import duty. But you can just transmit from these things, and you can measure all the parameters about them. You measure how wide a bit is, you measure what pattern is coming out. This is from a tool called Universal Radio Hacker that allows you to quickly take a software-defined radio recording of the signal and then chop it up and figure out what it should be at the physical layer. You then get modem configuration register values. So you give the chip this set. All of these numbers were first tried out in Python and only moved to the radio firmware after I knew that they were right. Again, minimizing the pain of figuring out which piece might be broken in a system that has many different moving parts. You then record the packets themselves. So this is 4 packets for the 4 buttons of the radio remote control. And then my watch is able to move this relay controller wirelessly by recreating the signal of the original remote control. With a bit more work, I might be able to make this learn it on the fly, and then copy remotes willy-nilly. Just to be clear, this does not use rolling codes. You have to pay extra for those. It's also kind of handy to be able to measure the frequency of something, right? So, for example, I was at the Troopers conference, and they had handheld radios that they were using to talk among the staff. So we got a software-defined radio out, like a HackRF or an EDIS USRP or something, and we measured what the frequencies were, and then we programmed those into my radio, and then I was able to talk to the staff, and it was fun, right? But this involved a lot of custom hardware. So I implemented the same feature to run in the regular watch. So now the watch can learn the transmit frequency of whatever the nearest transmitter is, just by running through the different channels and seeing which one has the highest signal strength. I bought a new radio, the one on the left. It came with no documentation except for like a Chinese battery disposal warning. And I promised the People's Republic of China that I will properly dispose of the battery. But I needed to know its frequency. So I just held it transmitting right next to my watch, and the watch told me that it was at 450 megahertz. It was actually at 450 megahertz.050. But it got me right in the neighborhood of it, and then I was able to communicate with this cheap radio that I bought without having to bring out any expensive radio equipment. I didn't need to take out a laptop. I didn't need to do any of that stuff because the watch that was already on my wrist was able to figure out the information for me. At the next conference that I went to, at B-Sides Knoxville, I wanted to copy their event radios. This was a bit more complicated because they didn't know their own frequencies. But my watch was able to find the frequency for me, and then I could happily talk back and forth with the staff. I could request a beer as I was on stage. I could do whatever I needed to. All because I had a nifty little watch that I built thanks to reverse engineering and a side project. If you're interested in this, the hardware design, the source code, the assembly guides, the documentation, the comments, all of it's available on GitHub or at goodwatch.org. And I'd especially like to thank SkyT, who financed this by paying me $30 for every month that I was unemployed over this past year. Can we get a round of applause for SkyT? I'm 1 minute over time, and this is Ruger, and Ruger is a very good dog. Thank you kindly.
Questions?
Sorry, it's just a technical design question. Do you have any theories about why the power requirement was so high for receivers? Is it something to do with the needing to load up the secondary oscillator or something?
I think it's that when you're not amplifying the signal, when you're not transmitting at anything more than the bare minimum of the oscillator is basically all of your cost. And the cost at the lowest power setting is identical for receiving and transmitting. So I believe the reasoning is that you're not trying too hard to push it out into the air, you're just sort of making the oscillator and hoping that it jumps into the air, and that the power requirement is the same one way or the other. So the instantaneous current cost is a little bit lower for receiving. It's just that when you stretch it out over time, when you try to listen for a message and you don't know when that message will come in, that's when it becomes really invasively expensive. I believe that the watch would die after a day or two in receive mode if I left the receiver on. To combat this, the watch has like, a watchdog timer. So if you're in any energy-using application for too long, which is to say anything except for the clock or the timer, after 3 minutes, it times out, kills whatever you're in, shuts down the radio, and moves back to the clock mode. And this has been working rather well, with the exception of a few features that are hard to turn off. Like the analog to digital converter needs to be shut down one step at a time. You can't just write zeros to its status register. I babbled for a bit, but I hope that answers your question. Oh.
I have a question.
Yes.
Is Ruger and consequently this bar somewhere in Montreal, or are you just telling me about your dog? Because I want to meet him.
Okay, so if you want to meet Ruger, go to the Crafty Bastard Brewing Company on Central Avenue in Knoxville, Tennessee. And you can ask for him by name as Ruger if you remember it. If you can't, you can just ask for the big white dog. Or more likely than not, you're going to trip over him as you try to get to the bar, because he's a very serious regular. He has his birthday party at the bar every year. Like I said, he's not my dog, but he is a very good dog.
I was curious if you were sweeping, doing a frequency sweep, what the battery cost was to do a full range sweep.
So the battery cost is more a moment of like more a function of how long you're sweeping. So retuning, I believe, does not have any particular cost of its own. I can perform this sweep in, I believe, a second and a half if I limit it to just the UHF band from 400 to 480 megahertz. So that's like a second and a half out of hours of radio budget that I have. And it's not a serious problem. I've recently added support for measuring the battery voltage so that I can recognize when the watch is no longer sufficiently powered to run the radio, but is able to keep time. And this should strike a balance where the advanced features will sort of gracefully degrade without crashing the device.
After all of your nifty utilities, how much space do you have left?
So I have scripts that keep track of this for me. So some friends of mine have contributed their own applications to it, and some of these take very little code and others take a lot of code, right? So you need to know not only like what features are currently, or how much space you have available, but you also need to know like what can be turned off in order to free up how much space. For example, Alexander Nikolic has been playing around with like password generators for it. These require a database of words in order to render the password on the display. That database takes space. So I wrote a quick Python elf script that runs through either an executable or a library module. And for that module, we'll tell you how much data memory is used, how much code memory is used, and also BSS. The other reason why you really want a script like this is that as C programmers, we're kind of lazy about where we put our const keywords. And if you put them in the wrong spots, you'll wind up consuming RAM for things that you don't actively change. And anything that you're not going to change really needs to be constant so that it only costs you code memory and not also a second copy in RAM as the application loads. I believe in the current implementation, we're using about 80% of the available code memory, and we're using something like 100 bytes of the 4 kilobytes of RAM. The other nifty thing that you can do with the linking script is that in the superior model of this chip, the 6147, you can actually turn off all of RAM except for 128 bytes that are specially battery-backed. And by doing this, you're able to not pay their static electricity cost. So you can maybe take down the 5 microamps a little bit and increase your battery life. Cool. Right.
In case there are no more questions, maybe I can get a last one. Oh, is there someone? Okay.
Aren't the watch bases out of print?
No. As best I can tell, all of these watches that were ever made were made in 2008. This is a modern design, not the one that you would have as a kid. You can buy these on Amazon. They're about $15. Again, for those of you in Europe, to import it, it's about 50 euro. Plus VAT. But they're easily available. You can get them in a rubber model, in a metal model. The black metal ones do not work as antennas, so don't buy those. Cool. And the last question?
How many batteries were killed during this project?
How many what?
Batteries were killed.
Quite a few. If you turn a feature on and you don't turn it off, you have a dead watch, and the log dies with it, so you don't know why it died. The power consumption is finally stable. Just to check, I have a watch cabinet with 12 of these things running different firmware versions, showing their voltages. And I watch them tick down, and I make sure that they're going slowly enough. Before I was that diligent about it, I would come home, and my watch would be dead, and I wouldn't know why. Bugs become a lot harder to track down when they're over a long scale. If my watch dies after a month, that's a failure, but it's a failure that takes a month to reproduce. I hope to save the rest of you the pain. If you want to make your own watch, please fork my firmware. If you do, you owe me 2 beers. I know this is not GPL compatible, but I hope you can forgive me for that. Thank you kindly.